Thomas and Sérgio on collapsed Anosov flows. And Thomas told me that he's writing in general a little bit with slow letters, so maybe you could come closer.
What I actually told him is I write like crap, but he didn't want to say that. So if you want to be able to read anything, you should come closer, but you don't have to. You can just listen, and that should be fine, I guess. Thanks for the organizer. It's my first Beyond conference, actually. So the aim of this mini course, so joint with Sérgio, and what we're going to talk about is results joint mainly with Raphael and some other people, but mostly it's joint work with Raphael Potri and Sérgio Fenley. And so the goal of this mini course is to introduce a class of partially hyperbolic systems in dimension 3. Also, yeah, maybe I'm going to start with that. We took M is always for me and for the rest of the course going to be closed 3 manifold, right? Closed 3 manifold. Because I don't know any other dimension. And so the aim is to talk about a class of partially hyperbolic systems on 3 manifolds, and convince you that this class is interesting. And this class is what we're going to call collapse Anosov flows. So they're collapse Anosov flows, but they are just partially hyperbolic diffeomorphism. And we want to convince you that they're interesting in kind of 3 ways. First, we want to tell you that they represent a large class in the world of partially hyperbolic diffeo in 3 manifolds, and large in lots of ways that we'll explain. So they're going to be large by saying that they're open and closed in the space of partially hyperbolic. So they contain the whole connected component of stuff. In some case, Raphael and Sérgio proved that all of them. And in general, we know that all the examples that we know of are of this class. So that's going to be one of the goals. The other goal is to tell you that even if you don't care about the classification of partially hyperbolic, which is kind of what this comes from, you may care about the dynamics of partially hyperbolic systems. And using this class, you can even deduce some things about the dynamics of it. So say accessibility of ergodicity, and that's another thing we'll try to talk about. And then lastly, it is something, sorry. It is something that gives you, so this class is also something that's going to give you a way of trying to find the missing partially hyperbolic systems. So we have lots of examples. We know some examples, but when we'll see with this class that there's some examples that may be there that we haven't proved existence of yet. So all of this is going to be the plan for this talk. And from now on, I'm going to start giving definitions. So let's start it. Oh, another thing that I'm going to say is, as a standing assumption, I don't want my manifold to have a pi1 that is solvable, because some stuff that we're going to say are probably going to be wrong in that case. So I don't want tori bundles, and then everything that we say should be true, except all the mistakes that I'm going to say in between. Okay, so setup. We start with definition. So I just heard that I don't have to define partially hyperbolic. So cool. I'm not going to define partially hyperbolic then. But anyway, so we have partially hyperbolic. Then I guess I don't have to define Anosov flows either. Yeah. Okay. So I'm going to define some stuff. Okay. So for us, F is going to be, so it's a partially hyperbolic diffeo if you have df invariant splitting, splitting of the tension manifolds and the tension space in ES plus EC plus EU. I mean, this is mainly for the notations. So where you have the stable that expands, the unstable that, the stable that expands in the past and stable that expands in the future, and the middle that does whatever, but in between the two. And we have, and I'm not going to write the actual definition because that's okay, right? And we're going to say, so smooth Anosov flow for us. Am I allowed to talk about uniform hyperbolicity in this conference? Or I'm not going to be invited anymore, right? So it's going to be a smooth Anosov flow if you have the invariant splitting, d phi t invariant splitting in, so same in the stable bundle. Now the direction of the flow, which I guess you can write it, d phi t dt plus EU with the usual expansion and contraction uniform. And so some things about, foliations. We know in general that for diffeomorphisms, partially hyperbolic diffeomorphisms, the strong stable is integrable and the strong unstable is integrable, but generally not the weak stable or the center stable or the center unstable. For the Anosov flow, for the smooth flows, you have the strong stable that is integrable, the strong unstable that is integrable, and obviously the orbit of the flow, but also the weak stable and weak unstable. And then I'm going to just give notations. I think Sérgio, we said that it was FS and FU for, okay. So I'm going to call FS the weak stable foliation. And FU, the weak unstable. And here's maybe something slightly more new to some people. In our context, it's going to be important to leave the world of smooth Anosov flows and go to the world of topological Anosov flows. So I'm going to give you a definition of this one also, or a fake definition. Well, I can give you a true definition if somebody wants. So M in M is a topological Anosov flow now. Anosov flow. If you have those weak stable and unstable, but you don't have the splitting. So if it preserves two transverse two-dimensional foliations, Fs and Fu, and those foliations are saturated by the orbits of the flow, and that on the stable, well, the orbits, goes towards the same direction in the future, and they need to separate a little bit, at least in the past. And on the unstable, they separate a little bit at least in the future, and need to go towards the same point in the past. Okay. So what that tells us is that, so in particular in this setup of topological Anosov flow, you may not have strong stable or strong unstable foliations. And another thing that I should mention, I mean, it's an old question of knowing whether topological Anosov flows can always be, made to be smooth, always orbit equivalent to a smooth one. So this was solved by Mario Shannon for transitive ones. It's still open for non-transitive, but even for transitive Anosov flows in this kind of thing that we're going to do, it's useful for the proof to go first through the world of topological Anosov flows. One more comment about topological Anosov flows that is annoying in in our papers. Those foliations for smooth Anosov flows are nice, meaning that leaf-wise, the leaves are at least C1. You can choose them to be even smooth. Right. In this setup, I didn't ask anything for the leaves of the stable and the unstable foliation. I may not know anything. So those are continuous foliations with a priori only continuous leaves. Okay. So that leads to some difficulties. We can show that you can assume to at least one of them to have smooth leaves, but that's all we can show. Okay, but so that leads to some difficulty, but that's the way it is. Okay, so maybe first example of the type of partially hyperbolic that we're going to be interested in is well, if you start with a smooth Anosov flow and you take the time one map of it, you get partially hyperbolic, right? Fun fact, I don't know. Well, in general, that's not going to be true for topological as well. Yeah. Yes. So you preserve. So because of that, because of the dynamics, you can show that the same result holds. Okay. So if you've never seen those, you can really think that everything is the same as in the smooth Anosov flows, except there's some difficulties that you have to deal with. But this one is not. Most of the theory, so most of the topological theory of Anosov flows goes through topological Anosov flow with no change or very little changes. Oh, true. So if you have a transitive topological Anosov flow, it is orbit equivalent to a transitive smooth Anosov flow. Yeah. Okay, well, that leads me to a next definition, orbit equivalence. So we're going to say that phi1, if I have two flows, phi1t and phi2t, two flows on M, flows are orbit equivalent if I have a homeo, if there exists H from M to M, a homeo, sending oriented orbits to oriented orbits, right? Oriented orbits here. Of phi1 to oriented orbits. Of phi2. Okay, this you knew, but I needed to introduce self-orbit equivalence. So H is a self-orbit equivalence of a flow phi t. Well, if it's an orbit equivalence between phi t and itself. Okay, so in another way, if it is an orbit equivalence between phi t and itself. Phi t and itself. So those self-orbit equivalents are the symmetries of the foliations by orbits. Why do I introduce all that? Now that we have that, we can actually start the course. I want to introduce what are collapse Anosov flows. So here's the first maybe new definition. Collapse Anosov flows are going to be partially hyperbolic diffeomorphism. They are related to self-orbit equivalence of an Anosov flow. And they're related in what way? They're semi-conjugated. And they're going to be semi-conjugated with an additional property. So partially hyperbolic diffeomorphism F is called a collapsed Anosov flow if there exists H. That's how we write, yeah. So H. Okay. Just going to change my notations here. In this mini course, I'm supposed to call those beta. Because this H is not self-orbit equivalence. So if there exists an H from M to M that is continuous, surjective, homotopic to identity, so I need this, a flow, a topological Anosov flow, phi t from M to M, and a self-orbit equivalence of phi t, a self-orbit equivalence beta from M to M of phi t, such that I'm going to semi-conjugate the self-orbit equivalence with this. So, and I have to do it in the right direction. So H goes from the Anosov flow to the. So what do I do? If I do the self-orbit equivalence first, and then I push by H, it would be the same as doing H. And then I apply them. Okay. So for every X, well, 1M. So I have that, yeah? Questions? What is phi? Phi is my topological Anosov flow, and beta is the self-orbit equivalence of phi. Okay? So I have, yeah. So, yeah. Yeah. Yes. The self-orbit equivalence sends orbits of the flow to orbits of that same flow. It's a symmetry. It's the symmetries of the, yes. Yeah, in general, except, well, you prompt me to define here. Let's add it. The thing that you had in mind were the trivial self-orbit equivalence. A SOE is called trivial. I'm going to do some examples right after I finish the definition. And maybe it's going to be helpful. It's called trivial. SOE beta is called trivial if, well, if it fixes every orbit, which equivalently means that it just, beta is just like pushing by that flow for some time. If there exists a map tau from M to R such that beta of X is equal to phi of tau of X. Okay. So the trivial ones are the ones that fixes every orbit, just change the parametrization, cool. But there's some more a priori, there should be some more. And we'll see that actually self-orbit equivalence of Anosov flows are very common. There's a lot of them. So there's a lot of symmetries for the foliation by orbits for Anosov flow. which is what those ones are. Okay, so yes. Smoothness of the flow is fine. What you're not allowed to allow is smoothness of the self-orbital currents. So then if you ask for smoothness, then there's not much. There can be a few, but no, well, maybe we'll get into that. Probably not. So I can tell you, if you want for C1, then for instance, in a mapping class group, they have to be finite order. So they're very uncommon somehow. Okay. Yes, more questions. Well, yes and no. If you remove the homotopic to identity, it somehow moves into this beta. So it's better to ask for this to be homotopic to identity and then fix your beta, right? Because otherwise you would allow to move in different classes of self-orbital currents, which is okay. Beta can be the identity. Beta could be the identity. Why would H not be the identity? Well, then, I mean, then F is not going to be partially hyperbolic. In general, H could be the identity. In general, beta could be the identity. If you want both of them to be the identity, that's too much to ask, right? There's some examples. So let me give, I'll just finish the definition and then I'll give some examples where beta is the identity or H is the identity or whatever, okay? If that. So this is not quite strong enough for a definition. I mean, it's strong enough, but not for us. You can say we're not smart enough to do it this way. So let's add something. Or I'm not strong enough. Maybe Raphael and Sérgio are. I'll let them judge. So we do ask that somehow the flow direction of phi t and the central direction of F are connected. So I want that H sends the flow direction to the central direction. And that's my second condition. So H is differentiable along orbits of phi t. And if you do H star of d phi t or t, this lands in the central direction. Okay. So now that's our full definition of a collapse Anosov loop. I semi-conjugate with self-orbital coordinates, and I have a control of the central direction of flow is sent to the central direction of the partially hyperbolic. So let's give some examples. Yeah. Oh yeah. Yeah, maybe I should have said my topological Anosov flows are at least differentiable. They're generated by a vector field, by a continuous vector field. H is surjective, but not necessarily injective. So H can collapse several orbits of the flow. No, not in this. It's transversally. You could have several different orbits of the flow that gives like center curves that merge, because you have that merging in partially hyperbolic in general, and we'll see that also. Okay, yeah, but yeah, the collapse of the names comes from you may have like orbits of this flow that are sent to some central curve that happens to merge, because you can do that in partial hyperbolic. Is that okay? Okay, examples. And wait. Oh, yes. Thank you. Yes, the collapse is in transverse direction. Yeah, yeah, exactly. Okay, examples. Well, my favorite one. If IT is a smooth Anosov flow, then phi1 is a collapse Anosov flow with, well, the flow phi t, the h being the identity. For instance, well, it's flow phi t, flow phi t, h the identity, and beta equal to p1. Or if you prefer, that was for the, I can have h the identity, right? Whatever I want. Or if you prefer, I could take beta to be the identity and then change my h. Well, h to be 5, whatever it needs to be. Okay. So this is, so in particular, so phi1 is a CAF with a trivial self-orbital covariance. Okay. This is trivial because it doesn't change the orbits. It fixes every single orbit. Okay, this is actually a type of class of, so the CAF with trivial SOE that's been studied under different names by different people. And I'm going to give you our name because, you know, I'm allowed to do that, right? So we call those discretized Anosov flows. So as a sub-definition, a partially hyperbolic f from M to M is called discretized Anosov flow if f is a CAF with trivial self-orbital covariance. Okay, so that was the first example, not particularly interesting. You can do slightly more interesting examples by you start with the phi1 and then you deform it, right? You do some little change of time-on map of an Anosov flow and you still stay in this class of discretized Anosov flow, the collapse Anosov flow with a trivial S. Let's go to a slightly less trivial example. And way less trivial examples. If you have, we're going back to, if you have a symmetry that is smooth enough, you can act by the symmetry and then compose by the flow and get a partially hyperbolic system. And that was the examples of Bonatti and Wilkinson. Bonatti. Some of the examples that they did in their, I believe, first paper on the subject. So suppose you have beta that is C1 and self-orbit equivalence of an Anosov flow, a smooth Anosov flow. Then, if you look at if you look at the composition of beta and, well, maybe for this example, let's do it even nicer than that. Let's assume that it really commutes. So it's really a symmetry of the Anosov flow. I take an actual symmetry. Take a symmetry. And I'll give you a way of building such an example in a second. And then you can look at then beta composed with phi 1 is a CA. Right? Because beta doesn't do anything to the stable direction, doesn't do anything to the unstable direction, doesn't do anything to the central direction. So if you hit it with phi 1, you get something that preserves the partially hyperbolic. So how do you build some examples like that? And that was in Bonatti and Wilkinson's paper. Is, well, you start with a geodesic flow that has some symmetries. So the example of the example is take a surface sigma with a hyperbolic metric G, so hyperbolic surface, such that there exists sigma from a little sigma from sigma to big sigma, an isometry of G, and then if you take the derivative of sigma, this is from T1 sigma to T1 sigma is a symmetry of the geodesic flow. T from T1 sigma to T1 sigma. Okay. So if you start with the symmetry on your surface, you get a symmetry on the tangent, unit tangent bundle, and then you can compose the two and you win. We do P sigma composed with G1 is a collapse Anosov flow. And what is the self-orbit equivalence here? Well, it's just D sigma. This flow GT and SOE D sigma. Does that make sense? So symmetries of the flow, if they're smooth enough, right here everything is very smooth, leads to these examples of collapse Anosov. And as I mentioned just before, the problem is in general, those SOE are not smooth. There's lots of self-orbit equivalence, but they're very rarely smooth. So you can't do just that. And I guess the surprise that led to these definitions and to this paper was the fact that, well, all the examples of partially hyperbolic diffeomorphisms that were built are secretly have this symmetry of an Anosov flows in them. So somehow all of them are built on that model, and we'll get the criterion that gives you that. That is due to Bonatti, Gogolev, Hammer-Linden, and Potry. And all of them has this hidden symmetry of an Anosov flows behind. So that's where we are heading. Okay. a simple proof that every partially hyperbolic is a collapsed Anosov flow? Where does it fail? Oh, everywhere. I mean, like you start with a partially hyperbolic diffeomorphism. First, you don't know that the manifold supports an Anosov flow. Okay, so you don't have foliations. You don't have a model to compare to. You don't have anything. It's very difficult. And in general, we don't know how to do it, right? We have some cases where we can do it. For instance, on hyperbolic three manifolds, we can prove that, but it's a lot of work. It's a lot of, you start with some tools that we're going to introduce, branching foliations, showing that you have something that looks like a partial, an Anosov flow in the background, prove some conditions on how the center directions behaves on the weak center stable leaves and all that. And finally get to that point. There's no simple proof. I don't think that there's any hope of having a simple proof, but again, that might be stupid. It's not even true. I mean, yeah, but I said that I threw away all those manifolds where it's not true. So yeah, if you have, you can find some counterexamples on T3 or skew-products over T2. So on those, when you have a torus bundles, you can make some things that do not fit in this category. Yeah. No. Oh, a simple example with collapse. At the fourth lecture, I will give you some examples with collapse. Because simple, no. I mean, it's not obvious that it's collapse because you have to show that you have that the example. So yeah, there's like several things to show, right? You have to show that you have examples, that they're collapsed Anosov flows, and that the examples you have are not dynamically coherent. And that leads you to the fact that this must be collapsed, but there's not a simple example either. It's not. Well, we'll probably get to there eventually, but yeah. Yeah. Yes. So that's where that's you know, in my hand-wavy plan, I said that this definition gives you a way of trying to find the new partially hyperbolic that we're missing. It's easier to build. I mean, it's not too difficult now with some tools we have to find self-orbit equivalence of an Anosov flow. The problem is they're not smooth, and so you can't just do this trick. And you have to prove that you can deform them to something smooth that would preserve a criterion that we'll get to. And if you have that criterion, then you can use that criterion of BGHP and get some Anosov, some partially hyperbolic, and then we know that they are collapsed Anosov flows. But it's a lot of work to go from a self-orbit equivalence to actually building a collapsed Anosov flow. It's actually very difficult. You had a question also before, or? Okay, no questions? No. A simple one? No. No, a priori, we don't have a criterion. I mean, we have lots. Well, we'll see that we have lots of definitions that we can prove are equivalent. So there's some other definitions that are somehow easier to realize. And that's how we prove that those examples are collapsed Anosov flows. But there's no, at least as far as I know, there's no simple example. It would be great to have a simple criterion. Yeah. What is the advantage? Well, because somehow, so it gives you a way of classifying. So there's several things, right? There's the classification question. I do classify. If I know that I have a collapsed Anosov flows, then I'm left with classifying Anosov flows, which was the original questions on classification of partially hyperbolic. So we know, I mean, there's lots of criterions to tell you when an Anosov flow is transitive. You can, I mean, there's lots of ways to see when an Anosov flow is transitive. There's some results like accessibility we'll talk about. You can show accessibility or ergodicity of collapsed Anosov flows, just assuming that the flow is transitive and that that the non-wandering set is everything. So this is a class that can be useful, and that's the thing that we're going to try to do. So it's useful in terms of classification because it tells you if one can show that every partially hyperbolic is a collapsed Anosov flow, then you reduce the question of classifying partially hyperbolic to classifying Anosov flows and self-orbital equivalent, which is, you know, it's not complete, but it's far along. And then even if you don't care about the classification question, using the dynamic of the flow, using some stuff that you know about dynamics of Anosov flows, allows you to deduce some things about the dynamics of the self-orbital partially hyperbolic. In particular, ergodicity or accessibility, you can attain that. Okay. More questions? All good? Okay. So, oops. Okay. So now that I have one definition, I need to tell you more definitions. How long do I have? 5 minutes. Oh. Oh, no, I need to stop it. Okay. Whoa. So one definition today. No, I'll keep that. Let me give you more definitions. So maybe so that we can start working. So okay, so as I said, this definition is somehow still weak in the sense that we know what happens to the central direction, right? The direction of the flow is sent to the direction of the center. However, we don't know what happens to the weak stable direction or the weak unstable direction. That is not included in this definition. Maybe you could have that the weak stable plane is sent to something completely different, or the weak stable foliation is sent to something completely different. What we have as a next definition, as a stronger class of collapsed Anosov flows, is something that's going to encompass this added property. I want to control not just the direction of the flow of the center. I want to say that, you know, the weak stable foliation and weak unstable foliation behaves more or less nicely. Okay? And in 2 minutes, okay, I'm going to define branching foliations. So the problem is no control on H of Fs or H of M. So how to fix that? I need another definition, and I'm probably going to I'll stop here with the definition. So branching foliations. Branching foliations. So think of it as a foliation that is allowed to merge. I have leaves everywhere, but instead of being always nicely stacked, like a normal foliation, like a nicely behaved foliation, some may merge. And that's not so fun, but it's okay. Okay. So branching foliation is going to be, it's enough to think about it as just like a foliation, but with leaves that are allowed to merge. And the theorem of Burago and Ivanov, well, there's two theorems of Burago and Ivanov. Is that if F is partially hyperbolic with orientable bundles, to assume that ES, EU, and EC are all orientable, then there exists branching foliation. I'm going to call WCU, WCS, branching foliations that are tangent to EC plus ES and EC plus EU. It's obviously the opposite order. That wouldn't be fun otherwise. And invariant by F. With orientable bundles, that's only the power. Oh yes, so yeah, sorry. F with orientable bundle and preserving and F preserving orientation. So invariant by F. Okay, so this is one of the fundamental theorem for the study of partially hyperbolic using the techniques of foliations that were used to study Anosov flows. And another fundamental theorem, still by Burago and Ivanov, tells you that branching foliations, you can actually approximate them by true foliations. And this is what allows you to bring a lot of techniques of true foliations to the study of branching foliations. And I'm going to stop there, and Sérgio will have to do everything. Thank you.
More questions, please?
For Zoom participants to hear.
On me, I'm old.
The definitions that you've given all seem to make sense in any dimension. So is the theorem, the couple of theorems that we heard at the end, is that sort of where three-dimensionality kicks in?
Mm-hmm. Yeah. So the definition makes sense, except we don't know much about, and by much I really mean that we don't know anything about Anosov flows in higher dimension, and we don't know existence of self-orbit equivalence. However, let me advertise the work of Santiago Martincic that I talked somewhere about discretized Anosov flows. So those discretized Anosov flows is those partially hyperbolic, which are associated with collapse Anosov flow with a trivial beta. And so Santiago proved a lot of results about those discretized Anosov flows in any dimension. So it's a beautiful paper. You should look at it. Yeah, and actually, and it has even a nicer definition than this. So you don't have to assume that the flow is Anosov, which is great.
Thank you.
So if we want to,
when you gave the definition of collapse Anosov flow, you say that either H or beta could be the identity.
Yeah.
But how is it possible that beta be the identity? Because it is not.
Okay, it's not.
No.
Well, what do you mean? Oh, no, beta can't. Yeah, sorry. Yes, beta
Okay.
can't be the identity. H
Okay.
can.
Thank you.
Yes. Because you can't, yes, because otherwise, yeah, we can't do that. Well, yeah, if otherwise you have F composed with H is equal to H, which I think it's hard to get the partial hyperbolicity. Yeah.
Yeah.
Fair enough. Thank you. That was really the only stupid thing I said. That's pretty good, right?
Maybe I allow myself with a comment answering to some of the questions here about definition and so on. So in 2000, Enrique Pujals proposed that all partially hyperbolic on any three manifold was in some sense related to either Anosov map on T3, either the product of Anosov on T2 times some skew product with the rotations on the circle, or with the time one of Anosov flow. So in his meaning, it was, I think, we tried with EMI to make a true conjecture using these constructions there, that it was alternative. And then we have make example breaking completely this conjecture. And in fact, it's my great surprise that they have been able to give back meaning of this relation between partially hyperbolic on either the two other case or with Anosov flow, with this notion of collapsed Anosov flow. And for the moment, there is no more counterexample to this possibility. So, okay, it's a complicated definition. We have difficulty. We are not specialists to understand this definition, but it's an amazing attempt to yes. So sorry. Let's sound Thomas again.
Right.